Thank you for the introduction. I want to talk you through the use of traffic conflict technique when assessing 2+1 roads. This is a study as part of a READ project with Dr. Shagawa as the leader of that project, and we joined forces with international partners. So this is really a continuation of a previous report which I presented at a previous Gambit conference. So more and more often we take the proactive approach where we don't want to wait for accidents to happen, and instead we want to know about traffic safety in advance, and we want to define this based on road user behavior. And it is a lengthy process to wait for accidents, and this is why we took steps to estimate how to identify conflicts using different methods. Our goal was to apply different approaches. We already had traffic counts for 2+1, and so we focused on those sections, and our main focus was on where those lanes terminate, because that means aggressive lane changing, increase in conflicts. So what were the objectives of our research? First of all, it was to assess traffic conflicts. We began with observed conflicts and then moved on to simulated ones. It involved microsimulation, and we used driving simulators. Well, observation is time-consuming, as we all know, when it comes to real traffic conflicts. So simulation came in very handy, because that way we were able to translate real conflicts into simulated conflicts, whether it's just simulation or driving simulations. Well, a main problem is how to validate the results. And so in the paper I'm presenting, the main problem was about how to validate this and compare real conflicts with simulated conflicts using different methods. So as I said before, this refers to 2+1 roads in Poland. Now on to the method. Well, it's pretty simple. What I mean is that we observed conflicts using video footage, several hours of video footage, and we observed vehicle trajectory in the merging area on 2+1 roads. We also used microsimulation, as I said, using the VZIM software, a well-known software. And we also use the experience from our international colleagues. So when it comes to conflicts, in each case we would extrapolate vehicle trajectories, and we use that to identify the intermediate measures for assessing road safety. And those were the typical measures, which is post-encroachment time, which is the time it takes to get to the point where a collision could happen, and time to collision, which is a better indicator, because it helps to identify vehicle behavior, and would the conflict happen if the drivers change their behavior. So we would identify these, not in all of the environments, however, but when it comes to observation, that's PET and TTC, those were the values that we observed each time. So for simulated conflicts, we used the software called SSAM, which really helps us to use data from microsimulation to assess vehicle trajectories and to determine conflicts for pairs of vehicles. And it's both for time to collision and PET. And we would analyze the conflicts for 1 second to less than 5 seconds. 5 seconds is quite a lot. So we compared the number of conflicts. Less than 1 second, that's something we didn't look at because we think that would be that's possibly too much error there. And the idea of simulation is to learn from that and include that in design solutions by doing this in advance rather than doing something in practice and then watching and observing, because it takes time and money. So simulation and driving simulators are a way to cut costs. And so we would change traffic volumes, the length of lanes and of the merging lane. By doing this, we were able to carry out a big number of simulations, more than 55 scenarios, 5-hour simulations. I don't want to go into the details of this, and it's already covered in another publication. Now, observed conflicts, that's quite simple. We had cameras up on masts, then watching vehicles. We first did pre-selection, where we would first pre-select vehicles that are close to one another, and then each image was analyzed frame by frame, 25 frames per second. We would then identify the trajectories and come up with these time to collision and PET indicators. So that way we knew the number of conflicts and the real number, but not just the number, but also the value of the conflicts. Here is a summary table of the number of conflicts. It doesn't look like much, but it took a lot of time to arrive at this. Some observations take a long time, while there are some automatic methods, but they don't yield good results. And some of the methods are semi-automatic, and we use those as well. The number of conflicts here is tied to traffic volumes for different cross-sections. You may be familiar with the cross-sections. On these sites, we have different intervals and different volumes of heavy vehicles. And then our goal was to understand the relation between observed and simulated conflicts. We didn't really have many sites, but the correlation is this: some 10% of conflicts, 0.1 times the number of observed conflicts. That's the number of simulated conflicts. So the relation is 1:10. The location of the conflicts, well, you can see this in this picture here. Most of the conflicts happen on the merging lane. And when we did microsimulation, we saw that conflicts usually happen at the merging of the lanes, something we didn't see earlier on. So driving simulator, as I said, we ran the test in Rome, where they have a full cab Toyota Auris driving simulator. And it's used for research objectives, but it's also used by students. And so we had a cooperation there regarding this to do the analysis. So they've been working in Rome for quite a long time, looking at traffic condition assessment on specific sections. So the system is very well calibrated and the team are very experienced. This is a real picture, and that's on the left, and and then to the left, you can see the simulated situation, and again, real and simulated. So we've recreated the situation exactly as it is in Kraśnik and in Piaski. Both are 2+1 sections. And based on that, we conducted tests involving 40 people. The age average is pretty low, 26. That's because we had a number of students. A downside of the study is that this was done in Italy, where 2+1 cross-sections aren't very popular. But everything was recreated, and the same people drove across it several times, and so they were getting accustomed to that cross-section. So we compared speeds at the beginning and the end of the overtaking lane, and we compared real and simulated results. We have high consistency there. In one case, initially it's 2 kilometers per hour, and it's at the end of the additional lane, it's around 4 kilometers, which suggests that the results are reliable. Because it's a driving simulator, we were able to analyze speed, acceleration, vehicle position, making it easier to recreate the trajectory and whatever happens later on. We measured the post-encroachment time and compared it with the data from observation. Well, we didn't really compare the values. Instead, we compared how the PET values are distributed. The variability range was at up to 3.5 seconds. That was the threshold. And that's based on traffic observation, not simulation, because that would be a higher value. And we had a separate simulation for the two sides. As it says here, it included 99% of the detected conflicts. I can't give you a number for that, however. I don't remember that. When it comes to the results themselves, looking at this distribution, you can see that for the two sides where we have observed results and the Piaski results, the shape of the distribuant is pretty similar, and the shift is parallel shift. It's at 0.3 seconds. With the Kraśnik side, quite off. Looking at PET. Now, what's the reason for this? Maybe it's the spacing of the poles. There aren't any in Kraśnik, but the observed conflicts came from each of the sides. The conclusions, as I said before, comparing simulated and observed conflicts, well, it seems that there is this linear correlation, and the relation is 1 to 10, meaning a big difference, which again means that this is not a simple conversion between simulated and real conflicts. The driving simulator, the observation only covered the distribution of data. Our sample wasn't just big enough, and so we decided to compare the distribuants, and we only compared PET, even though the data are available. But to do it for TTC is difficult because it takes time, and so we haven't done it yet. The results are quite promising. When you look at the Piaski results of observed conflicts, there is this parallel shift, and it seems that data from the driving simulator could equally be used to estimate conflicts. However, it will take more work. And the Piaski side results are really surprising. The results, as I said, are promising, and it seems that both approaches could be applied to use the proactive approach as an intermediate measure of road safety until we are able to develop a real method. Well, there are many centers worldwide trying to develop the method, but still no final or best solutions available. What's important is to identify thresholds for the intermediate measures. That's something we haven't done. It will take more work, where we would like to know how many conflicts there are and how does that change from method to method and what are the actual values of the variability. Well, that's it from me.
Dziękuję
Thank you.
bardzo.